Welcome back. We're in circular motion. Worksheet number 2, problem number 4. We got this amusement park ride here. Now, if you've never seen one of these things before, let me go show you what this is going to be like. Narrate over this. It doesn't have to go up like this, but the point is that as this starts to rotate here, you can kind of see, as it gets faster and faster and faster, these occupants here, the ends of the swing here, they swing outwards, as you can kind of see there. And so if it rotated even faster, they would swing outwards even more. And at the end, when it stops swinging there, which is somewhere in here-ish, as it starts to slow down here, the angle of those swings going out there decreases and becomes more and more vertical. So we're looking at that. Hey, why does that happen? Why do they swing outwards there in the first place? Now you can see that it's really starting to slow down, and those strings there that are holding them up are just vertical there. So what's going on with that? And now this one doesn't actually go wrong. That's just some silly clickbait that they have for people, but it's perfect for exactly what I wanted to show there. Anyways, so let's go and let's see what's going on with the physics here. So the setup, we have the length of this string, this chain that's holding them up there is 10 meters. The top of the disc is 8 meters in radius here. So I'm going to start listing this out. Let's say that that's the center right there. And then the radius here is 8. And these are all in SI units here, so I don't have to change anything. The angle is in 20 degrees from the vertical. And so I measure something from the vertical to that chain in this case here, and that's 20 degrees. Using the diagram below for one of the chairs, determine the period of rotation. So we're looking for capital T, the period there is a big question mark. And the magnitude of the tension force in the chains of the chain and rider combination has that mass here. So that's mass. And I'm looking for... And now, see, if I did T for the tension force, that's going to be very confusing with my period there. So I'm going to go ahead and I'm not going to use T for the tension force, but I'm going to use F sub T for my tension force there and say that's a big question mark because that's what we're actually trying to find. So what am I going to do? Well, I could do anything that I wanted to, obviously, but I noticed that the rider in the chair has a combination of 120 kilograms, so I'm given that. And furthermore, I'm looking at the relationship of this rider and the rest of the ride here and the angle that they're at and such, and going, hey, I can make my system that rider and the chair there. And if I did that, let's go ahead and let's see what the forces are going to be on that. Now, if I did look at those forces, I could also see that the tension is going to be on them, and that's what I'm trying to solve for. So it looks like that might work out. So what forces do I have on it? Well, I have the force of gravity, shunk, that goes down here. And then I got some tension that goes up at that angle there. So try to match that angle as best I can there. And again, I'm going to list that as F sub T there so I don't get confused with my period. And any other forces? Let's think. Contact forces. I have tension, normal force, and friction there. And so I go, well, I don't have any friction because I don't have any other surfaces pressed into it. So I don't have any normal forces either. So I only have tension there. And then range forces, I got the force of gravity, electromagnetic force. I don't have anything about charges in here. Nuclear weak and nuclear strong, it happens, but it's inside my system here. These are internal forces, so I don't have to worry about them. All right, so then I only have those two forces that I can identify there. So I guess those are my only two forces. I compare that to my coordinate plane, and I should drop a coordinate plane here. So let's go do that as well. I go from this perspective right here, I'm going to say that this is going to be one axis, and this one would make sense to be the other axis here. And I think about that, and I go, okay, now I could call this the X and Y axis here, but now that would work for this specific position. But then what if it was like over here or in the back over there? Then the X dimension wouldn't be as useful. But if I pinned this coordinate plane directly on my system here, then this would be the radial dimension. Notice it's pointing radially inwards from the circle that they're making there. And so that would be the positive radial dimension, and this would be the negative radial dimension. Now, the other one, we usually do radial and tangential dimension, but now check this out. Which way is this going in this picture right here? Well, it depends on which way we have this thing rotating here. Does it even say? I don't think it says. So we can kind of choose. If it goes this way, that means that the chair is coming out at us right now. So that's not, so up and down is not the tangential dimension. This would be like the y dimension there. I'd have to draw another view to be able to see the tangential dimension. And I could do that if I wanted to, and maybe I'll do that in a little bit, and because that might be helpful. Actually, I'm going to go do that right now because I bet it will be helpful, and it's good to get in that habit there as well. Oh, so that's we have a side view right here. Hello. This is a side view that we are given already here. So let's go look at a top view. Now, it's going to be a little bit hard to draw these different perspectives here, but let's do our best. We're going to imagine that we're in like a helicopter looking straight down at this thing. What would we see? Well, I'd see the top of this disc of the ride there. And I know that this disc has this radius that is 8 meters. Okay, great. What else would I see? Well, notice that they're at this like angle here. So for them at that point right there, you'd have like the rope, and the rope comes out a little bit, and then you would see the top of this box, which just looks like another box there then. And so they would be like seated there, somewhere in there. Okay, so I'd have multiple of these going around there, but we're only looking at this one right now. So it would have something like that. Now, this blue thing is my system, and so I'm going to go ahead and I'm going to draw the path that it would take there. And as that thing rotates there, the path that this is going to take is some circular path there. Okay, cool. And so if I look at my coordinate plane, now I can pin my coordinate plane directly on here, and I could see that I'd have a tangential dimension there, and I'd have a radial dimension here. Positive radius and negative. Okay, cool. So now let's think about that. Okay, great. It's going around this circle. How big is the circle in which it goes around? I go, well, that's easy. I just measure the radius from here to here. But the radius from here to here, that's the blue dashed line is supposed to be a perfect circle. The radius from here to here is not 8 meters. It's like 8 meters plus a little bit more. Well, how would I do that? Well, I look over at my triangle here, and I go, maybe I could like get that from my triangle here. And this is a physical length. I'm trying to figure out this physical length, like right here. What is that physical length there? Well, that's just a mathematical length of that rope there. And so I go, okay, that's 20 degrees there. That means that must be 20 degrees right there. Alternate interior angles. And so now this side over here is going to be L, and that's going to be the opposite side. So L sine of 20 degrees is going to be the length of that side there. So that means that this portion over here is 8, and then this blue portion right here is L sine 20 degrees. Okay, so then like the total radius here, maybe I'll do like capital R for this new radius here, that'd be capital R, will be 8 plus L sine of 20 degrees. Okay, great. I'm thinking about all that because it's probably going to come into play there since we're looking at the acceleration, how that relates to the velocity squared over the radius there. So yeah, okay, so great. Back to my free body diagram though. I got my coordinate planes now. Now I have all 3 axes that I've listed out here. And I am still comparing my free body diagram to my coordinate planes here and going, hey, in the y dimension, I have a little bit that goes in the radial dimension and a little bit that goes in the y dimension there. I should probably split that tension up into both of those there. And sure enough, let's go ahead and let's do that. So I have 20 degrees in there. That's alternate interior angles there. And so now here I have Ft is times the sine of 20 degrees, and this is Ft times the cosine of 20 degrees. Okay. I think about that and I go, okay, great. At this constant radius, we're assuming that it's going at a constant rate of rotation. And so it is a constant radius because it's a constant rate of rotation. So it's sticking to that one angle there. That means that in the vertical dimension, let's go ahead and let's sum up these forces in the y dimension here. And I go, what forces do I have? Well, I look at my free body diagram. I got something pointing up there. That is Ft cosine of 20 degrees is pointing up. And then I have mg, which is pointing down, and that's equal to m times a. Now I think about that and I go, okay, what's my acceleration going vertically upwards and vertically downwards? Well, it's rotating at this constant rate here. So this angle that the swing swings out at is constant. And so it's not accelerating up, nor is it accelerating down, which means that this acceleration in the vertical dimension, remember that this is the acceleration in the vertical dimension because we're working in the vertical dimension, must be zero. Another way to say that is that my forces are going to be balanced in the vertical dimension there. So it's going to be Ft cosine 20 degrees is just going to be the same value as the force of gravity. Okay, cool. Maybe that'll come in handy later. I don't know. I could even go and put tick marks on this stuff and go, that's the same size as that one there. Okay. Then I go, okay, well, what's causing it to go in a circle? I know that it must be accelerating to the left-hand side. How do I know it's accelerating to the left in this picture? Well, that's centripetal, that's radially inwards there. And anytime I'm going in a circular path there, I know that I must be accelerating because I'm changing my velocity, right? My velocity is pointing tangential at every point there. And so the tangential velocity is constantly changing directions. Or in comparison to the actual tangential dimension, it's always going in the tangential dimension. So it's the same direction relative to our coordinate plane, which is the tangential dimension there. Tangential axis anyways. So, but it is changing, the velocity is changing the angle, you might say, that it's at there. So it is accelerating inwards. Well, if it's accelerating inwards, then there must be some force that's providing that to make that happen. There must be some force that's causing it to accelerate inwards. And check that out. We have a radial force here. That force is pointing to the left there, which is radially inwards there. So let's go ahead and let's sum up the forces in the radial dimension here and see what happens. So let's look in the radial dimension, sum up those forces there. And I go, okay, I have Ft sine 20 degrees. Is that positive or negative? It's pointing to the left, which is in the positive radial dimension. It's pointing towards the center of the circle, towards the center of the circle here. And we always say that towards the center of the circle is positive there. Is equal to m times a. Now, I know that this a refers to an acceleration that is centripetal here, pointing radially inwards. And so that's equal to the tangential velocity squared over the radius there. So I can go and put that in, and maybe that'll help me out here. So that's Vt squared divided by the radius is equal to my tension force multiplied by 20 degrees there. Let's think. What do we know here? Well, do I know the radius? Yeah, I do know the radius because I know that that's 10 there. So boom, I got that. Okay, that's cool. So I know the radius. Do I know the tension? No, I don't know the tension. Actually, that's one of the things that I'm trying to solve for. So I am trying to solve for the tension there, and I'm also trying to solve for the period of this ride here as well. Well, let's go ahead and let's solve for the tension and see what we get here. So I'm going to go ahead and I'm going to do Ft is equal to, I'm going to move that sine of 20 degrees to the other side, mvt squared over r times the sine of 20 degrees. I just divided by the sine of 20 degrees there. And then go, okay, great. Do I know the mass? Yes. Do I know the radius? Yes. Sine of 20? Got that. Do I know how fast this thing is going? Well, it doesn't tell me the velocity here. I go reread the problem. It doesn't tell me the velocity there. So let's think about that. So I go and I think about it and I go, well, I know it's going in a circle here, and I know the path that it takes there is 2 pi r, and that r is capital R as I defined there, the total radius that this thing is going in. And so it's going that distance for every 1 revolution per my time that it takes to go around there. So maybe I could put that in. Maybe that'll help me out. Maybe. Let's go ahead and let's do that. Now, that's true for my tangential velocity. Now, careful, we're going to go and square that there because algebra says to go and square that. So I have my Ft, and that's equal to m. Now, that's all of that 4 pi squared. Don't forget to square that pi. That's an easy one to miss there. Times the radius squared divided by what radius is this? So this is the radius which is relating to this acceleration. That's the acceleration of my system here, which is actually capital R. So I should have recorded that as capital R at the beginning there, and that should be capital R there as well. And so that means I have capital R here divided by t squared. Don't forget to square everything both in the numerator and denominator there. Now, does that help out? Well, let's see. One of the r's cancels out there, and I have ft is equal to that big jazz there. Let's go ahead and let's rewrite that. So I have 4 pi squared r times m divided by my period squared. Now, do I know these values? 4, yes. Pi, yeah. R, yes. M, yes. T, I don't know that. Ft, I don't know that. But wait, hold on a second. I do have one equation here with 2 variables, and I have one equation over here with 2 variables. Maybe you caught this earlier on. Maybe you didn't catch it till now. But I look at this and I go, wait, m times g, I know that, and I know cosine of 20. That's easy. Actually, I could have just solved straight away for my tension force up here. Notice, let's go ahead and let's do that. That was 120 times 9.8 divided by the cosine of 20 degrees. And that will tell me what my tension force is there. Oh, that would have maybe changed how I did things over here, but that's okay. We figured it out now. So let's go do that. I got 120 times 9.8, and I take that and I divide it by the cosine of 20 degrees. And I make sure that I'm in degrees there, and sure enough, I am in degrees there, and I press enter. And I get 1251.47 there. I'm going to go store that. That's my tension there, so I'm going to store that as T so I don't forget what it is. And then if I need to use that again, which I probably will, I'll have that there. So 1251.47. 1251.47. We know in newtons there because both of these values were SI units. Okay, that means that over here, I'm actually solving for t squared there. So let's go ahead and let's just rearrange that there. I'm going to multiply by t squared, divide by my tension there. And so I'll have t squared is equal to 4 pi squared r times m over my tension force there. Now, I know that I need to find t, not t squared, so I'm going to go ahead and straight away I'm going to take the square root of all that, which then undoes that square there. And so now I have what t is. Now I can put in, I have all these values here. Let's go ahead and let's put these values in. 4 pi squared, I know what those are. R was my 8 meters plus, going back up here, R was my 8 meters, right? It was how big that top of the ride is, plus the little length of string that was swung out there, L sine 20. Remember that L was 10 there, right? And so then it's 8 plus 10 sine 20. So I get plus 10 sine of 20 degrees. And then multiplied by my mass there, which is 120. Divided by my tension force, which is the 1251.47. Again, I'm not going to use a rounded value when I go and calculate that. No. I will use the full string of values there. Now, you could also take this and plug in mg over cosine 20 and just plug that in for there. And actually, let's actually go and do that. I'm going to go ahead and I'm going to backtrack a step here. And I'm going to take this thing and I'm going to plug it in for there. Why am I going to do that? I want to check this out. You could solve this problem without doing that, but you might miss something. Check this out. 4 pi squared r times m over, now let me recopy that. That's mg divided by the cosine of 20 degrees. Let me clean that up a little bit because I got a fraction in the denominator there. That cosine 20 is going to flip up to the top there, divided by a fraction there. That's the same thing as multiplying by the reciprocal of the fraction. And so that means that I'm going to have 4 pi squared r m times the cosine of 20 degrees divided by mg. Wait a second. Hold on. I see that I have m there and m there. Oh, wait, the mass cancels out. I don't even need the mass there. The mass doesn't matter. wait, hold on. That means that at the beginning of this problem, they didn't even need to give you the mass. You could have done this without the mass. And notice that the video confirms this as well. This means that the period that it goes around and the tension and the angle is independent of the mass here. The mass doesn't affect the angle that it's at or the period or any of this other stuff. And if we look back at the video here, that we can see that that's true. It's approximately the same angle for all of these guys. I don't see one way further out than another as it goes along here. And clearly all these people have different masses. And so we know that they are independent of the mass. We have evidence for that. And sure enough, it comes out to be independent of mass. That's really nice. Now notice that if I didn't do that, if I just did it like this, I would have solved the problem, but I would have missed that deeper truth there. And so this is part of the reason why I encourage you to do things with variables. And so when I go in, I'll go ahead and I'll do that over here because it's a little bit simpler now that we already did that. And I'm going to erase this bit so my equal signs don't get mixed up here. And careful, we are solving for the period. Capital T is period in this case because we already said the tension was F sub T there. So let's go ahead and let's take the square root of all this stuff. 4 squared. The radius here was 8 plus my 10 sine of 20 degrees times the cosine of 20 degrees divided by 9.8, which is G there. So let me go grab my calculator. And now I have my tension there, but I don't even need to use it when I go and plug this stuff in. So I'm going to go and see if I can get it all in one line here. So I'm going to take the square root of, do I need parentheses around that? No, I don't. 4 pi squared. I'm just following order of operations, as your calculator is always going to follow order of operations. 8 plus 10 sine, oh, I didn't get the 10 there. 10 sine of 20 degrees. Close those two parentheses, keep that all together there because we wanted to add all of this stuff first. Times the cosine of 20 degrees. End parentheses there. Then take and divide that by 9.8. Now notice I didn't need parentheses for the numerator there because all of these things are, besides the thing in parentheses there, all of these things are multiplied by one another. So that's the same order as this division that's right here. And the tiebreaker for the same order is left to right. So I know that it's going to do all this stuff on the left. Then it'll take and divide that by 9.8. If I had more than one term in the denominator there, then yeah, I would need to make, or more than one number in the denominator, I would need to put that in parentheses there. So I'm going to do that first. Press enter, and boom, I get my period here. Oh, and I didn't memorize that number there. Is 6.58 there, 6.58. And that must be in seconds since that is SI units there. And SI units is in seconds there. And I did square the pi. That's an easy one to miss there. And the radius is just to this first power. And I'm just double checking myself as always there. So I think about that and I go, that's pretty quick. But is that too quick? 6.5 seconds? And I don't know, get some ride here. And if I time that 1, 2, 3, that's probably actually faster than 6 seconds. So it seems like 6 seconds is a reasonable thing. And we can even time that down there. So yeah, 6.5 seconds is definitely not too fast for something like this. And it doesn't seem too slow either. So it seems like it's probably reasonable value there. Good. So we just figured out the tension force. Good. We needed to do that. We figured out the period there. Good. We needed to do that. Reread the problem. Make sure we didn't miss anything else. The period of rotation of the ride. Got that. And the magnitude of the tension force in the chair, and the rider has that mass there. That's it. Hope you have a beautiful day. I will see you later. Bye.